Good morning, my name is Mohand Hamadouche, a PhD student at UBO France, and today I'm here to present you our work on a reward tuning for self-adaptive policy in MDP based distributed decision making to ensure a safe mission planning. For this, I divided my presentation into 5 parts: context and motivation, decision making based on MDP, a method principles, a case study, then I will finish with a conclusion and perspectives. Markov decision process become a standard model for a sequential decision making under uncertainty. However, in several fields, such as in robotics, several actions can be performed simultaneously. Moreover, with the increase of the complexity of missions, the decomposition of an MDP into several sub-MDPs becomes necessary. This decomposition involves parallel decisions, but the execution of concurrent actions can lead to conflicts. In addition, malfunctioning system and sensor failures may appear during this mission and lead to negative consequences. In this systematic review, we found some works like 1, 6, 7, but they don't guarantee an appropriate choice of the action for a safe mission, and/or they don't take into account the resource constraints. Works in line, their method can be applied only for the collision avoidance in the case of trajectory planning. So our contribution are the resolution of behavior conflicts between several MDPs, the introduction of safety rule, the proposition of a systematic method to define, then adapt the rewards in order to modify a policy. Markov decision process models a dynamic process. The environment is observed in each step by the agent. It selects an action, then performs the action selected, then the agent receives a reward. The policy P is a solution of an MDP, and is also a decision plan that can be invoked at any time. It determines for an agent at each state the action that should be carried out. The optimal policy P star is the policy that corresponds to the expected total reward received by an agent starting from the state S, like this formula. Here we can see an example of decision making, which is the forest management, where we have 2 objectives: maintain an old forest for a wildlife and make money by selling cut wood. We have 3 states representing age classes and 2 actions, wait and cut, with the following probabilities and reward matrices. Rewards are given to actions in a way that allows trees to age before being cut. The resolution of this MDP gives us this policy. In the case of distributed decision making, we have to manage the conflicts, so we distinguish 2 types of constraints. Constraint associated to the behavior conflicts, for example, the return to home action and the tracking action are antagonist actions. We have also constraint on the system or on the sensor health, for example, if probability of detection of obstacle by lidar higher than threshold, so we prefer the avoidance obstacles action than other actions. Also, we define the notion of policy priority in order to manage the adaptation of policies. First, a static policy priority, where the priority is determined offline and remains stable throughout the decision process. We have also a dynamic policy priority, where the priority is determined online and dynamically adapted to the context of the mission. Here we illustrate the reward adaptation with the management of several forest problem. we have two forests. We solved the MDPs and we found these policies. We consider the constraint impossible to execute action 1 simultaneously between the two forests for the age class 1. We define a static policy priority. For example, priority of policy 1 is higher than the policy 2. These policies are obtained from the formula 2. To modify the policy 2, we will recalculate the reward of the action 2 in the forest 2 using this formula. In the case study, we consider the tracking mission where the UAV follows a predefined trajectory. Upon arrival at the search area, the UAV tracks the potential target when if it is detected. The mission is defined with three main MDPs. MDP navigation with the actions of navigation and safety. MDP landing with actions required for landing. Then MDP tracking with the different algorithmic version of the tracking application. Here we can see the overall actions of the global mission. In this case, to manage the conflicts, first we enumerate behavior conflicts, then we identify the conflicting states, finally we add the NOP action to these states. Here we can see the graphical representation of the three MDPs and on the right the policies resulting from their resolution. Also we can see the conflicting states marked with the red stars. To avoid the conflicts, we define policy priority according to probability of good health of the system and the probability of good obstacle detection. We can see in the table the MDP which receives the highest priority according to the two criteria chosen. To validate the method, we elaborate three scenarios. In scenario 1, we have a proper functioning of the system and without obstacles on the trajectory. We solved the MDPs and we found these policies given in figure 6. In figure 7, we can see the resulting policies after solving conflicts. In scenario 2, an obstacle appearing on the trajectory, so we change the probability of obstacle detection with the LiDAR to 85%, initially 13. We solved the MDPs and we found the policies given in figure 6. In figure 8, we can see the resulting policies after solving conflicts. In scenario 3, the system is degrading, for example, battery malfunction, so we change the probability of good health of the system to 29, initially 19. Then we solve the MDPs and we found the policies given in figure 6. In figure 9, we can see the resulting policies after solving conflicts. To conclude, the MDPs are used to present sequential decision making. However, in the literature, the rewards are mainly given in a random way and stay fixed during the decision process. In this work, we propose a new method allowing us to automatically set rewards. This method is able to avoid the violation of constraints and identify behavior conflicts, then succeed in solving these conflicts. As the future works, we propose an implementation on real autonomous UAV and extend the method in the case of collaborative swarm of UAVs. Thank you for your time.